This is lecture 17, and in lecture 17 we're going to get back to unsupervised learning, and we're going to talk about clustering today. Before talking about clustering though, I wanted to just kind of get us back into the mood for unsupervised learning. So I just wanted to kind of frame the whole supervised, unsupervised learning in kind of a probabilistic way, or a statistical way. After all, this is kind of statistical learning. So in a supervised problem, we have some y, and typically that's just some number. In a regression problem or in a classification problem, y is going to belong to some set of classes, and we have some set of data or a particular data point, let's say y x, and x is, let's say, some set of numbers in RP. And if we think about it from a statistical viewpoint, if I view my pair x, y as random, then they have some joint distribution, and we could denote that joint distribution maybe as p xy. And supervised learning is basically some kind of density estimation problem. Is basically density estimation where we want to estimate, say, p of y given x. So this is kind of the central quantity in supervised learning that we want to estimate, which is the likelihood or the probability of seeing a y given a x. And if we can kind of figure out what that probability is, we can estimate y. For example, often we don't even want this whole distribution. We just want maybe some mean or some f, where f minimizes overall, or say f hat minimizes overall possible f's, some loss of f, or some expected loss of f, where we look at the expected value of y given x, and we did this whole derivation for squared error loss. You can basically view it as we want to choose f to minimize kind of our expected loss of y given x. And this whole thing is just some mean we're estimating. In any case, what we want to do in a supervised problem is either we want to kind of say something about the conditional density of py given x, or we want to estimate some property of it, maybe some particular mean, the expected value over y given x of maybe the loss of something, and we want to know something about that. We're going to maximize it or minimize it somehow. So that's basically supervised learning in a nutshell. Of course, Bayes' theorem says that we can, of course, write our joint density, p of xy, as p of y given x times p of x. And for supervised, we're interested in this, in p of y given x, and not so much p of x. We don't particularly, in and of itself, care that much directly about p of x. Sometimes we can use it to get p of y given x, but the kind of real central thing that we're interested in is p of y given x. Unsupervised learning is basically the opposite. Learning. For unsupervised learning, we just have some p-dimensional x's. So we just have x. We don't have any y. And so we're not looking at some kind of conditional distribution. We're not trying to determine some kind of conditional distribution or estimate the conditional density of y given x. We want to estimate basically the density of x, p of x. And I could say estimate, or we could say summarize. So this is kind of a very statistical way of viewing this, right? So you could say that, okay, unsupervised learning space, I'm trying to learn something about the x's, summarize the x's. From a statistical viewpoint, I'm just trying to somehow describe p of x. So while supervised learning is looking at p of y given x, it doesn't care as much about p of x, unsupervised learning is basically looking at p of x. There is no kind of corresponding p of y given x because we don't have another set of variables y's to condition that we can condition on our x's, right? So all we want to do is unsupervised basically estimate this p of x or summarize it in some way, all right? Because that's, of course, if you have a random variable x, a statistician would say, well, what summarizes it? Well, the distribution of it. So the kind of quirks, let's say quirks of unsupervised learning is that there's a couple of things to note here. There's no direct measure of success. And there's no it's no loss function we're minimizing. We don't have, the supervised learning. You imagine you have an algorithm and you're the teacher, you're supervising it, and you're going to teach it, right? You're going to give it examples and it's going to make some predictions, and then you know the answers and you're going to, whack it on the wrist, whack it on the knuckles and say, no, that's wrong, and it will learn what the right answers are, right? So you're kind of the teacher and the algorithm's the student, and you're supervising, you're teaching it, right? And in the unsupervised case, you don't have a set of y's you're trying to predict, and so you don't have a kind of truth to what the correct way to summarize things are. All you have are the x's, and you're trying to summarize it, and there's no real direct measure. Say, oh, you got 5 of these wrong, or you got these wrong by, my RSS was 10, right? And so what this has led to is there's a lot of different methods, and it's a bit subjective about, about how well unsupervised technique works and how do you measure whether an unsupervised technique works. So it makes us a bit uncomfortable because as kind of mathy people, there's no kind of real hard way of measuring it. Nonetheless, it's a super important problem to solve. So let's say there's no direct measure, many methods. Let's say, so there are many methods out there and opinions on what methods are good, what methods are bad, etc. But ultimately, what we want to do is we want to summarize this density of x. That's a kind of statistical viewpoint. You could just say summarize x, but as kind of a statistical viewpoint here, a probabilistic viewpoint, summarize something about p of x. So how can we do that? If now we have our capital P, which is the number of variables, is low, so we're basically in a low dimensional problem, we could directly estimate density of x. We could estimate it, we could visualize it. We could form a density estimate. We could make a histogram. That's basically a one-dimensional estimate of the distribution. You could make a box plot, right? So you could visualize it, you could estimate it. Now that will work if P is low, but it's going to be kind of complicated to do that and visualize correctly if P is high. And so if P is high, what do? We could look at summary stats. Or we could use something like PCA, which is one way to view PCA is basically is trying to find a low dimensional subspace or a low dimensional subspace that contains high density that contains the high density parts of P of X. So the idea is that one way to view PCA, I said there's about 100 ways of viewing PCA, is one is that if I have data points that kind of, maybe they actually live in 3 dimensions, but they kind of live in this flat pancake here. And you could say, well, I could basically summarize these by looking at the subspace that kind of best captures this flat pancake. That's basically saying that, my points technically live in a 3-dimensional space, but they're not really densely packed throughout that 3-dimensional space. Really, they're kind of densely packed throughout 2-dimensional space. So if I want to summarize my density function, P of X, I could find the subspace where that kind of captures the main kind of contours of that density. So that's definitely one way of measuring, of doing this. And a second method, and what we're going to talk about today, a whole second class of methods, is called clustering. And clustering, basically, the probabilistic way to view clustering is that basically it tries to find kind of convex sets of high density parts of P of X. So it basically tries to find kind of little sub-portions that are of P of X that are high density. And we're going to call these clusters. So one way to, kind of the more classic way, so that's a very probabilistic way, the classic way of understanding what clustering is that we want to create so-called clusters. Let's say within our data, so that points within a cluster are more similar to each other than points in different clusters. So basically, we're going to break up our data into a series of what we're calling clusters, or I'll call them groups occasionally. And what we want to have to be true is that the points within any of these groups or within any of these clusters are kind of more similar to each other than they are similar to things in other groups. So the kind of classic picture of this, so I can draw kind of an example. So here's my X space. Maybe I have, P is 2, I have X1 and X2. And here are my data points. This is kind of a pretty realistic, data set you can get. Okay, so there are my data points there, little X's there. Now, it's not like in a classification problem, because I don't have, this isn't training data. There's no concept of training data or testing data. In unsupervised learning, we just have We just have the x's. There's no y. So it's not like we have circles and triangles in this case. We just have some data in an x space. And to me, and probably to most other humans, it looks like there are two groups here. And so what we'd like clustering to do is to try to discover these groups, right? So in this case, you could probably do it basically by eye, but if you get to a 1,000-dimensional space, you're not going to be able to cluster things by eye, and you want to have some algorithm to do this automatically. Or if you have 10 million points, you're not going to be able to by hand cluster these things. But in this case, it looks like there's a cluster 1 and maybe a cluster 2. And what we'd like our clustering algorithm is to discover these clusters automatically. That is really not legible, is it? Let's try this again. Goal is to discover clusters automatically. Okay. Now, in this case, it's pretty obvious what the clusters are, but I could make this harder. What if I added a point like there, right? So now we have a question. What cluster does it go in? I could put it in my cluster 2. So my cluster 2 maybe looks like that. But it's also pretty close to cluster 1. And we don't have a truth. There is no ultimate metric that says this is right, this is wrong, this is the right clustering, this is the wrong clustering. It's not a supervised problem. And so there's a lot of different opinions, and you'll get different answers depending on what you use. But there's no kind of from on high answer that says, oh no, that one should actually have gone in this cluster as opposed to that cluster. Typically in complex problems, you don't have a real good answer for that. Okay. So for clustering, our goal with clustering, or the kind of heuristic way, is that we wanted to create clusters within our data so that the points within a cluster are more similar to each other than points in different clusters. So there's this word similar here. And basically what we need to do clustering is we need some measure of either similarity or dissimilarity. Because ultimately, what we want to do is we're going to create some algorithm that are going to put similar points together and keep dissimilar points apart. And so to do this, we need some measure of similarity between points, or conversely, dissimilarity between points. And so let's talk about similarity or dissimilarity. Ultimately, all clustering algorithms, or let's say almost all, they just need a measurement of similarity or dissimilarity between all points. Let me just stop there. So this is a really general framework. To do this clustering, we just need some measurement of similarity or dissimilarity between points. So if I have some capital N objects then we can form a matrix, let's say D, which is going to be an n by n matrix, so that if I look at the element I prime, if I look at some element of this matrix, this is going to be the dissimilarity between the ith and I prime object, let's say. You can alternatively, I will say parenthetically, if I have a measure of similarity, it's supposed to read similarity between objects, I can create D using a, say, decreasing transformation. So if instead I had some measurement of similarity between objects, I could just create this thing. I could just look at them decreasing. I could basically reverse order them. And then it would get dissimilarities. But what I haven't said here yet is that I need a covariant matrix. And the really interesting thing is that many / most clustering algorithms only need this dissimilarity matrix D. We don't even need some covariant matrix, some matrix X. So let's say normally the way we think of this is that we're going to have our objects, which are the rows, or n rows of X, and we've measured P features on this, and we have our X matrix, which is n by P. However, for a clustering algorithm, we don't even need to have that. We just need n objects, kind of very broadly, whatever that means, objects. And we just need some measurement, some matrix that says if I have the ith object and the I prime object, what's my dissimilarity between them? So I could come up with those. You could give me a set of objects, and I could just come up with numbers off the top of my head that measure dissimilarity, and we could give it to a clustering algorithm, and it could cluster those objects. I don't even need to have written down specifically. It could be my subjective opinion about how similar objects are. So it's a really, really nice kind of in general framework. There are some properties that are typically kind of required for this matrix D, but they're not particularly onerous in any way. So typically D is going to have zeros down the main diagonal. Which basically corresponds to that the dissimilarity between an object and itself is 0. Now there can be zeros elsewhere, if I really say that the dissimilarity between two different objects is 0, but certainly the dissimilarity of any object and itself is 0. Okay. Otherwise, we could just remake the dissimilarity metric so it's true. Secondly, if I look at the dissimilarity between I and I prime, so that's the I prime entry of this thing is typically, not always, but typically required to be positive. So we keep dissimilarities as positive numbers, which is not too bad or too onerous of a condition. And the third requirement typically of a dissimilarity matrix is that it's symmetric. So 0 is on the main diagonal, non-negative, and typically symmetric. So symmetry is just means our dissimilarity metric is not, like, dissimilarity between I and I prime is the same as dissimilarity between I prime and I, right? And any kind of notion of kind of distance or dissimilarity will typically satisfy this. So again, this seems like a very natural condition to require. So again, I've been pretty vague up to this point, and about what dissimilarities look like. And again, I could, if you give me a set of objects, I could come up with my subjective opinions as long as they satisfy these three conditions. That, you know, you could write this first one as the fact that dii is 0. So that objects have 0 dissimilarity with themselves, have a non-negative dissimilarity with anything else, and the dissimilarity metric is symmetric. As long as I come up with that, some dissimilarity that satisfies those rules, we can play games with clustering algorithms. Because basically, you'll see when we run the code that many of these algorithms, you don't pass it a covariate matrix, you just pass it a dissimilarity matrix. You don't even need to know about what the covariates are. It just needs to know something about a similarity metric. So it's really cool. And it leads to the really powerful generalizations of the methodology. However, if we have covariates, let's say features, so we have some n by p matrix X, we can, which is the kind of real typical case, let's be honest, we can use, or we can form, say, attribute-based dissimilarities, where basically we're going to use the differences or not between the features of various observations to calculate a dissimilarity. So i.e. use differences between features to calculate D. And one way we can write this is that dii prime, so the dissimilarity between I and I prime, you could calculate as some dissimilarity function between xi and xi prime. So here D is basically my dissimilarity function. And it's going to take in rows of my matrix, I and xi and xi prime. So these are rows I and I prime of my feature matrix, X. And typically the way this is done is we basically define some dissimilarity metric for each column. So you can call dj my dissimilarity measure for feature j. And so for each of the features, right, each of the columns of X is a feature, and so I can have a dissimilarity metric that's just looking at the difference between the ith and ith prime feature, and I can calculate this dissimilarity for the jth feature, and then I can basically sum this over all my features. So basically, you can come up with a sub-dissimilarity metrics for each feature, and then the dissimilarity metric overall between two observations is just the sum of the dissimilarity metrics. My caveat here is to be careful with scale. So we should be a bit careful with scale here, because it's possible that my dissimilarity metrics give me values on very different scales. So this is the kind of thing that you ran into, say, when you did PCA. If your features are measured on very different scales, maybe you standardized to deal with that. And if your dissimilarity metrics, you have numbers on very different scales, your DJs, your dissimilarity measure for the jth feature is a very different scale, outputs numbers in the hundreds, whereas the dissimilarity metric for some other feature outputs numbers in the tens. If I'm just going to sum these up, then some of these dissimilarity metrics may dominate others. Now, there are schemes where people will say, well, you should always somehow standardize these things or blah, blah, blah. In general, I'm not going to advocate for that, because in general, it's going to depend on this specific problem. Sometimes we should standardize these things so that our dissimilarity metrics are kind of commensurate, but sometimes doing that will hide the real interesting differences and dissimilarities between our features. So there isn't a one-size-fits-all solution here. Sometimes it's good to do, sometimes it's not good to do. So let's look at just some examples. We'll just look at a couple quick examples of these. So obviously of different DJs, if we have kind of numeric data, let's say numeric feature, then surely we could say that, so let's say our jth feature is numeric. Then if we have our dissimilarity metric, the jth feature, DJ, between, say, xi and xi prime, two different rows of my covariant matrix, or my X matrix, surely the easiest thing to do is I could just define this dissimilarity metric to be the difference between xij and xi prime j. And maybe we'd square this. So this is basically a Euclidean, maybe squared distance. So in this case, the dissimilarity metric is actually a distance. It's the Euclidean distance, which is kind of the supernatural thing to do. Now, if you use the word distance as a particular meaning mathematically, it satisfies the triangle inequality, blah, 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 blah. This is why we use the word dissimilarities. But in this case, this dissimilarity metric for numeric features is just going to be, say, the square of the distance. If you had all numeric features and you used Euclidean distance, Euclidean square distance on all your features j, then your overall dissimilarity, your dii prime, would just be the Euclidean distance between two rows, and everything would work out. And we'll look at that today. Other examples, if we have, say, ordinal data or an ordinal feature, so it's not numeric, but the ordering to it is meaningful. Oftentimes we could transform our ordinal levels to let's say transform the level I, or ith ordinal level, to I minus a half over m. If I have some capital M levels, you could do some kind of conversion like this. This is kind of a popular conversion. And then we could treat these as numeric, e.g. use Euclidean distance or something like that. So that's one way people deal with ordinal. There's a whole literature on how different measures. We're going to give you a sense. So if you have an ordinal feature, right, Now, if I have some of my columns of X are numeric and some of them are ordinal, then I'll use maybe the Euclidean distance on some, and my ordinal ones I'll use this other scheme. We'll convert it to this thing, and then I'll treat them as numeric. And so my overall dissimilarity measure between I and I prime will be, the sum of the Euclidean distances between the elements for the numeric ones plus the sum of this other kind of scheme for the ordinal features, and so forth and so forth. So you can get it kind of a mixing. This is kind of a general scheme where you can have mixed types of variables in your columns. If I have, let's say, categorical feature, so my jth feature is maybe categorical, there are, again, a ton of different metrics. The simplest is that I could say the dissimilarity metric for my jth feature between I, xi, and xi prime is just I'm going to look at xij, and I'm going to see is xij equal to xi prime j, and I'm going to say that's just the indicator of that. So that is 1 if they are the same, and 0 otherwise. So it's a kind of binary 0-1 metric. 1 if these things are the same metric, 0 same category or categorical feature, and 0 otherwise. But you can imagine there are about 1 million ways of coming up with different dissimilarity metrics and combining them to have an overall dissimilarity metric. You can even do weighted things. You can do lots of complicated things here. But ultimately, all we want at the end of the day is some kind of dissimilarity metric. Okay. So how can we use this dissimilarity metric to do some clustering? So let's talk about it. And so the kind of rest of the lecture is going to be generally talking about combinatorical algorithms, or combinatorical clustering algorithms. And in particular, we're going to talk about a particular algorithm called k-means. And combinatorical means that, at least for now, we're not going to treat these things as probabilistic. We're going to de-emphasize the probabilistic component. We'll potentially come back and talk about it if we have time, but we're going to de-emphasize that. We're going to kind of talk about it as just purely a combinatorical problem. So this is really in the realm of, say, Dr. Kincaid would be kind of more of an expert on this than I would be. Okay. So the deal with this combinatorical clustering, or any kind of clustering generally, is that what we're going to do is we're going to assume that our data comes from one of, say, k clusters, and I'm going to denote them G1 to GK. G for group. So you call them groups, you could call them clusters. I'll use both terms and use G's just because I don't want to use C. So we use that too much. So my group's G1 to GK. And what I want to do for my combinatorical clustering is assign each of my rows of my X matrix, each Xi, to some G, let's say little k. So one of my GK. And how am I going to do this assignment? Basically, I'm going to do this assignment to minimize let's say some degree or loss, I'll put that in quotes, some degree or let me say some degree, some measurement. Sometimes these are called losses of not being clustered. So that's basically right. What we want to do in clusters, we want to group our data into clusters so that things within a cluster are more similar to each other than things between clusters. And the way we're going to do this is we're going to do this to try to minimize some measure of things not being clustered. If I make a certain assignment, how unclustered are these things? And so the classic way to do this is called W, which is often called the within cluster dissimilarity, or the total within cluster dissimilarity. And basically what I'm going to do is I'm going to sum over all my clusters, 1 to capital K, and I'm going to sum over all pairs I prime in my cluster, GK, G little k, and I'm going to sum my dissimilarity metric. So what is this sum? This is basically total dissimilarity measure across elements in the same cluster. So this thing is a function, this W, this with total within cluster dissimilarity is basically a measure of, it's a function of my group assignments, okay, which I need to find good ones, but let's say we have a putative set of group assignments, some G's, and if I just look at all pairs in my putative clusters as they've been assigned, and I sum up all the dissimilarities, this should be small. So let's say should be small if clustered well, right? Because the dissimilarity between things within the same cluster should be small, and this should be large if not clustered well. And so the idea is basically we're trying to choose some groups, some clusters, some G's to minimize W, to minimize my total within cluster dissimilarity. So this is a very classic thing to do. Another way of viewing this is that if I let T be my kind of total dissimilarity, which is the sum over all pairs I prime. So this is my total dissimilarity across my n items. So I'm just literally going to sum up the elements of my matrix. Sometimes people divide this by half. It doesn't really matter. If you divide it by half, it's like just like the total. It doesn't matter. You could, because your matrix is symmetric, you're kind of double counting, but it's inconsequential. I can also define what is called B, which is between cluster, or maybe we'll call it total between cluster dissimilarity. And this is if I sum over all my clusters, 1K goes 1 to capital K, and I sum over, overall I in a particular cluster, and then I look at all I prime not in that cluster, and I sum up the dissimilarity. So this is basically the total dissimilarity between pairs in different clusters. Then we can note, or we can actually prove, might be a good homework assignment, is that T, my total dissimilarity, is W plus B. It's the within cluster dissimilarity plus the between cluster similarity. And so to find good, let's say G's, to find my good cluster assignments, we can do one of kind of two things. One, which is minimize W, or two, since W is T minus B, we can maximize B. So you can think of, these are mathematically equivalent. So you can think of this in two ways. One, which is I can minimize my within cluster dissimilarity, my total within cluster dissimilarity, or two, I can maximize my total between clusters similarity. So the kind of two ways to view this, let's see if I can draw a picture here. One way is I can assign my clusters so that basically you can think of dissimilarities as kind of distances, and in the numeric case, when we have numeric features, you can literally make them distances if you want. So one way is I could say I could draw these because I want these x's to be within each of these two clusters, say G1 and G2, to be very similar to each other. Or two, I could look at kind of the distance between these two clusters, kind of measured by the total distance. If I look at pairwise, one of these things in this cluster and one of these things in this cluster, and I do all the pairs, I can sum that up and look at how far away they are, and I want to maximize how far away these. So you could either think of it as maximize between, which you can think of as kind of maybe this red here, which is kind of measuring how separated my clusters are, or minimize W, which is kind of, you want to shrink those circles as much as possible so that things within my cluster are kind of similar or close in some kind of distance to each other. So the question is basically, how do we do this? How do I find my G's? How do I find my groups, my clusters? Ideally, we consider all possible G's. Unfortunately, this is not computationally tractable. If you have, for example, and it's a pretty complicated formula that should count this correctly, if I have, say, about 19 or say 20 observations, and I have, say, only 4 different clusters that I want to find, then the number of possible cluster assignments is based something like 10 to the 10. It's a huge number. And so this gets really fast. I mean, most of the data sets we're going to work with are having more than 19 observations. We're going to ask for more than, say, 4 clusters. So testing all possible clusters just out. It's going to be so computational and intractable that we can't just try everything. Although ideally that's the ideal solution. You can talk to Dr. Kincaid about ways that could be approximated or solved. He's done a lot of work in that area. But for us, since I'm a lowly statistician, I'm going to say our solution, as with many things in life, to solving these complicated problems, is just to have some greed. And we're going to take a greedy approach, which basically means we're going to do the locally best thing at each step. We're not going to worry if it finds the globally optimum solution. We're just going to do at each step what makes the most sense. And it's not going to be guaranteed to find the globally optimum solution, but it will find us some solution, and hopefully most of the time will work pretty well. So the particular example we're going to talk about today is called k-means. And this is a famous and very basic, but really great clustering algorithm. And today, we're going to talk about it where all features are numeric. And maybe next time we'll talk about what do we do if we don't have numeric features. But it's easiest and was originally developed when we just had numeric features. And furthermore, what we're going to say is that our dissimilarity, which I think I've been using capital D, hopefully. Probably I should be using capital D, right, for these. Yep. How do I define my dissimilarity matrix? Yeah, I should be using capital D. Let's just fix this real quick. So this should be capital D, right? This is my dissimilarity, right? Dissimilarity. Let's just be consistent here. Doesn't really matter, but I was using capital D for the matrix, so let's use capital D here. Okay. Sorry, so back to this. We're going to define our dissimilarity metric and therefore a dissimilarity matrix so that the I prime entry is just going to be the Euclidean distance between xi and xi prime, and we'll square it. So this is the squared Euclidean distance. And if all features are numeric, we can definitely do this. In this case, and I'm not going to go into, it's kind of just a boring algebra proof, we can show that our within cluster dissimilarities, if we use this particular metric, the squared Euclidean distance, we can show that our within cluster total within cluster dissimilarity is just going to be following. I'll write it down and then I'm going to explain what this is. Okay, so originally, let's just scroll back up to look at what W was to start off with, right? So W was our total within cluster dissimilarity. We summed over the K clusters, and then we summed over all pairs in the cluster, and we looked at the dissimilarity between them. So in this case, so let me just say, recall that W was the sum, and then we summed over pairs so we sum over the cluster and we sum over the pairs in the cluster, and we look at the dissimilarity between these pairs. If we're using a Euclidean distance, then in this case, this is the within cluster dissimilarity is the pairwise distance, let's say the total pairwise distance of points in a cluster. So we sum over all the clusters and we just look at the distance between points in the cluster, right? So we're using the Euclidean distance, the total dissimilarity, the total pairwise dissimilarity, the total pairwise distance. It turns out, if you use this Euclidean distance, and this is purely some algebra, be a good homework problem, would be you can show that is the same thing as summing over my clusters, and K here is going to be the number in my kth cluster, and we can then show that it is just the distance, so it's basically weighted by the number in the kth cluster, but it's this second part here is going to be the total distance of each of my points xi in my kth cluster from x bar k, which is the mean of the kth cluster. So my within cluster sum of my my within cluster dissimilarity, my total within cluster dissimilarity, is not only just the sum of the pairwise distances within the clusters, but you can also think of it as the distance, the total distance of each point from the mean of the cluster. So let me draw the picture, right? So there's two equivalent ways of viewing this. One, if I have a cluster that looks like this, I could look at pairwise distances, right? Something like this, right? I could look at sum up pairwise distances. And so distances and dissimilarities are equivalent. We have numeric, we're using the Euclidean. The other is if my cluster looks like this, I could calculate x bar, which is my mean, which is somewhere in between here. This is a multi-dimensional mean. And then I could look at the distance of each of my points from this mean. And so total distance of points to their cluster mean. And it turns out that in the Euclidean case, we can show these are equivalent formulations of W. And of course, our goal with clustering is to choose my G's, G1 to G capital K, so that we minimize W. And the way that there's a couple algorithms to do this. We're basically going to use a greedy algorithm to do this. And the classic way of doing this is called Lloyd's algorithm. So let's look at what Lloyd's algorithm is. Okay, so Lloyd's algorithm has a couple steps, has kind of three major steps. We're going to call step 0, and step 0 is the initialize step. And the initialize step says that we make initial and typically random guesses of the group means. And we're going to call these group means mu1 for group 1 all the way up to mu k for group k, and we're going to put a superscript 0 up here to denote that that this is at the 0th step. After the 0th step, we're going to loop over some iterations, and I'll say t is my iteration. T goes 1, 2, 3, 4, ... We're going to loop until we hit some convergence criterion, where at the tth iteration, we follow two steps. We first follow what's called an assignment step, and then subsequently, too, we're going to follow what's called an update step. Whoops, that's not how you spell update. Update step. So at the assignment step, we're going to assign each data point xi to the group with the closest mean, mu k at point t minus 1. So let's draw a picture of our step so far. So let's assume that we have some data that looks like this, right? We have two variables, x1 and x2. And at step 0, maybe we initialize, when we want to initialize our things to. Here's mu, we're going to say, let's say k is equal to 2. And mu1 of 0 maybe ends up there, and let's say mu2 of 0 ends up here. Okay, so that's the initial step. At the assignment step, we're going to assign each of our points, each of these x's here, to the group with the closest mean. So we're going to make some group assignments, and it looks like, I'm going to guess that these 2 points are closest to mu2, so we'll call this g2 at time 1. And the other points are closest to mu1, so we'll call these things g1 at time 1. So that's the assignment step. So I'm basically saying these 2 x's belong with group 1 or belong to this mean, same thing, or in these 4 belong to our second one. And so that's the assignment step. We assign our points to the closest mean, and then we do an update step where we recompute the mu's as the sample means of new assignments. So what we do is we say, sure, let's do it in black. So my group mean, I'm going to recalculate the mean. So the mean is basically going to be the central point. So for these 2 x's, this will be mu2 at time 1. And for these 4, the mean probably lies somewhere over here. Let's say this is mu1 at time 1, right? So the mean is the kind of the central point, the centroid. Okay. And I'm going to iterate now. So I've done my assignment step where I assign the x's to the closest mean, and then I do the update step where I recalculate the mean. So I move those means, and then I iterate. So I'm looping over this. That was iteration 1. At iteration 2, I'm going to do my assignment step and my update step. So my assignment step probably says, now I've forgotten about my mu zeros, and I have my mu1 at time 1 and mu2 at time 1. I'm going to assign my x's to the closest center, the closest mean. It looks like now these 3 x's go with mu2, and these 3 x's are closest to mu1. And so I do my assignment step, and then I would update, and I would say this would be mu, so I cross out mu1, and I say the new mu1 at time step 2 is there, which is kind of the middle point, the mean of those. And I'd cross out this, and I'd say my new mu2 at time 2 is going to be the center of those. And I update that, that's my update step, and then I iterate. Now, if you notice, I iterate next time, none of the assignments change. And I basically do this until your means don't change enough. Until my means stop moving. So at each step, you're going to recalculate your means, they'll move, but eventually these things will kind of stop moving, and we will eventually kind of converge to a solution. Hopefully it's a good solution. We'll talk next time about whether or not we're guaranteed a good solution. But that's basically the k-means algorithm. And that's all it is. So the reason we bring up this fact here about W is, and we'll talk about it next time, but you can see that this x bar here is basically the group mean. And so when to try and minimize this thing, we can basically view minimizing this thing as finding the group means, right? So we can play the game within cluster kind of total dissimilarity, which typically is kind of pairwise distances. We actually can just look at the distances of each of the points to the mean instead of that group. And so that's the game we play here, where we basically do this iterative thing where initially we guess the mean, and then we assign things to the closest mean that will get us a slightly better clustering, and then we update and we recompute the mean, and we assign to the new closest one, then we update, and then we do this till the means kind of stop moving. So we'll talk about next time about why this actually works and why this is actually minimizing, right? My claim here is that this is actually minimizing this W. We'll talk about it, why it's decreasing it. You might not find the global solution, but it's at least decreasing it. But at least heuristically, it's a pretty reasonable algorithm. And so notice this thing is some kind of greedy algorithm where we're just taking kind of a greedy step to the easiest thing at each point. And so we'll see next time that it's not necessarily going to give us the globally optimum solution, but it will give us it will typically, and there are some kind of variations on this, typically it gives us something that's quite good. Okay, so we're kind of at time there, so we'll stop here for today.